So it started for Truncate, and people who are on MS Teams, please speak up. I mean, just ask. I'm sorry, I don't always see or couldn't always see in the screen. Sorry for that. So why Truncate? Important point. The reason is, without further ado, Truncate is used so often, and you don't want to read or write every single time. Why? Because all Truncate says is that if I had a 100-byte file, now I'm truncating it to 50 bytes. The rest of the 50 bytes, it won't go into space, right? It will stay there, but someone else can use it. It's a free space. So you should not be you should not need to read and write and copy and doing all those heavy duty stuff by just changing the size of the file. Think about it. The size of the files is just a variable stored somewhere on your disk. So it Truncate does, it just changes the size, like the value of the size, nothing else. So Truncate, generally you either use a function called Truncate. I never use that function. I just use this reduction operator. So you can do echo null character and then redirect to nodes.h. It will just change the size. Also, you can do colon here and then redirect to the nodes.h. It will change the size to 0. However, those two that I told I use, they're always for create an empty file, like removing everything from a temp file or something. You need more heavy-duty Truncate when you try to actually resize the file, change the size. You can mention the size, like, just first 50 bytes. After that, it's free space. Now, these are basic operations, as I told, right? So what about copying a file? You can do it by using create, read, and write. Actually, create and write. You create a file and then create, read, and write. Sorry. You create a new file, you read from the old file, you write to the new file. If you want, for your own intellectual pleasure, think about the complex things that you do using single commands, and everything should be able to be done using these basic commands. Now, the example of using this command, there's a catch though. The example, like if you now think about when you start writing C programs, do you really start just writing to a file, like giving a path name? A file is just to you, it's just a path name, a full path of the file. Do you actually do that? Let's look into a C code, right? I mean, this is like the basic in PDS, like, you have a file *fp, and then somehow instead of reading or writing or doing anything useful, you start opening and then you start doing anything. Every single programming language does that. Even Swiss knife language like Python, you need to open a file. The reason is this abstraction about like any idea that why do we need to open? Of course, if you want to open, you also need to close. This is just a dual of each other. Why do you need open? Why can't we just read or write? I know that I want to read or write to a particular file location. Why can't we do that in the first line? You need to file descriptor. That's a heavy word. So essentially, you need a pointer to the file instead of saying descriptor, because descriptor has, yeah. But you're absolutely right. I mean, I'm saying it is absolutely right. But simply speaking, what Nisarg told, like you need a file descriptor to actually create a pointer to the file. The point is that moving deeper into it, the operating system needs to do bookkeeping. It needs to know that your process is opening a file, give you a pointer, and then keep track that your process is reading or writing to the file. And that bookkeeping is done on fopen. This is not for your convenience, this is for operating system's convenience, for keeping track of who is writing at what positions or reading from what positions. Essentially, due to this bookkeeping, like this is again, this is overhead on the user, right? They have to write one more line, but this is necessary. So these two ingredients, open and close, is used for all of this like these basic operations like read, write, create, and so on. Truncate, no, because you're just modifying the size, the exact size of the exact file. You're not really reading or writing any storage locations. So let's see what open and close actually does. And then Nisar possibly will talk about file descriptors. So if you just give open fi, which is that for fi for your purpose will be the file name. Remember the absolute and relative path that we talked about in the tree? If that file name does not start with a slash, that means that it's in the relative directory, same working directory. Operating system will take care of that, appending that PWD or client orchid directory before the name of the file. If not, it will be on this, it will actually use it as a full path. But either way, that full path does not mean anything. It's just a name given by you. So the first thing that the operating system needs to do is to search for that file in your directory structure that is on your disk to know what are the storage devices or storage locations. So first is search the directory structure of disk. And once the operating system, it actually switched to the kernel mode, right? Even during searching. Search the directory structure. Then check if the calling process actually have permission to even reading or writing or creating that file. Anything you want to do needs a permission. Permission is attached with your directory, with your file. We'll talk about it at the end a little bit more, but just assume that you might or might not have read or write permission to a file or directory. Operating system checks that. If all the checks pass, then it will go into actually creating the file descriptor mode. How? Essentially, then it starts its in-memory operations. So what the operating system does is that it will create an entry in the array of open files that is in memory for the OS. Operating system actually have one or more arrays of all the files those are open by all the processes in the system. This is for the bookkeeping. This is what the open is for. So when every check's passed, it adds an entry to that list or the array of the open files. And finally, it will return the index of that particular entry in that big array that is in the kernel space. And that index is your file descriptor. That's why I was saying that it's not really pointer, it's basically an index in an array. And from that, you can do the magic, like OS can do the magic. So this is yes.
Sir, it's not really an index, because if you open it is an index, but it's not. If you open a file in like 5 processes, then all of them will get FD3 because FDs are assigned in usually ascending order, and 0, 1, and 2 are already assigned for any process. So the first one will always be 3. So it is probably not an index into the global open files list.
They actually use relative positioning, but nonetheless, it is an index. You can think of it as a function of the index, because ultimately that has to be resolved to the index in the open file array, if that makes sense.
Right, but then like suppose if I do a dup call, then I can then I can have multiple indices that actually point to the same place.
Yes, that does. And then we'll talk about the array more. There is not one array.
I see. That makes sense.
Just give me like next slide. Okay, let me go to the next slide. But before that, once you open, you need to close. What does close mean? Close essentially means remove in-memory data structure. So essentially on disk, you cannot do anything. In memory, the operating system now knows that your process has done something. Now you want to close. Operating system will just remove that entry for your process. For your process, mind you. Because multiple programs can read a file or write to a file. So even if you closed, they have not. So that entry might not be removed from the operating system memory, but your process will lose pointer to it. Make sense? Good. Now let's go deep into it, because these things, they actually requires again overhead, again data structures, how they are implemented. Essentially, you need a couple more data structures for making this open happen. because this is just a bookkeeping operation for bringing correct directory structures and file pointers to the memory and then giving it to the process. So what are the data structures needed for each of the steps? First one is search the directory structure on disk. No data structures. The data is the tree structure is already there. Do a traversal. Cool, fine. But after that, you check the privilege of the process. That means those privilege needs to be stored somewhere. Correct? That means there is something called access rights, that is per process access mode information. What is per process? Essentially in Linux, whichever user calls a process, the process inherits the permission of that. So all the operating system needs to do is to store the user specific access with the file. Because otherwise you don't know who, anyone can open the file, security vulnerability, messing up, system will break. So first one is access rights. You need to store those bits with your files. So the second one is now going deep into the whole arrays, like array of the file descriptor in memory. So this is on disk, the access rights. Next one is in-memory data structure. Now, the next part is that creating an entry in the array of open files in the OS. So this is called open file table, which tracks the open files. Now, do you think this open file table is on the global system or per process? Does each process has its own open files or a whole global set of open files with a lot of processes written here, like process 1, process 2, process 3, open this open file or something? Which one do you think will be most efficient?
I would think both.
Processes having pointers to that particular.
Both correct? Actually, both are correct. Any case. So essentially, yes, absolutely. Both is implemented. First, the main data structure is a system-wide open file table, a huge one, okay? And then the process will just point to the open file table. It won't store anything. It will just be a pointer that which open file tables, like in that system-wide file table, which files are opened by this process. And that makes closing really easy, right? You just remove the per process pointer. The system open file table, that will remain intact until and unless the last pointer is removed. So we have open file table. It's basically a struct of arrays. Again, a memory location allocation where there are these kernel data structures. Nothing fancy. And finally, you actually need this file pointer of where to read and write within that file. You need that data structure also. You need to store up to which part this process has read or wrote that file. This has to be per process. That's why I told you it's an array of structs. It's not only the pointer to the global file table. You need process specific information stored with the process. So question? Yes.
So any two processes which do not share a parent-child relationship, can they share the same entry in the system-wide open file table?
Yeah.
They can.
They can. Think about it. You have two processes, or you and Rajat has two processes. You can open a file, open a file and start reading from that file in a shared system. Rajat can also do that.
But these exactly the same entry. So they'll have the same that offset of the pointer.
No, the offset will be stored with the processes. The offset is per process, right? Because you can read 3 lines and others can read 5 lines. Is it your question? Any other question? I have a question. That was actually, I asked in the last exam. If you have a parent and child, and then you forked essentially.
If one moves ahead, the other also moves ahead.
That
What?
If It doesn't move on.
It does.
It doesn't. The answer will be none of those. None of the.
They move along. Never common.
Like,
Go offset is not copy.
okay, so you have, okay, tell me there are two options. One, you know the question and you thought about the answer. Second, you just thought about right now. Both of them are very
We know the
interesting.
question.
Okay. Very interesting. Any idea why? Because that was just a question in an exam. I wanted to write a 2-line answer to it. I think I generally write 1 to 3 sentences, testing understanding. But now it's a class. Why? First, Ashutosh, you go. You seems like know the answer. So tell the
I
question.
don't know the answer. I knew that it happened. I learned.
What was the question then? I forgot it fully.
It's like if the parent is so like if I have a file A, B, C, D, E and my parent has read till D and then my child starts reading, it will start reading from E. That's what I have seen to happen.
Why? The why question was definitely not in the exam. It was just like starting a thinking process. But start intellectually thinking. Those people are just like you. First sitting in a classroom, then going to an industry, trying to write some code and take decisions. So why do you think that happens? Why don't the child starts? So the question is that if you have a process reading a file till line 40, then the process fork the child, whether that pointer in the child, whether that will start from 40 or from the beginning. This is one. And second, if the child parent pointer moves, whether the child pointer will also move. What is it expected behavior? Always start to think what is reasonable and expected behavior and then try to reason.
Can you repeat the first one?
The first one is that whether, like you understand, like parent and child, both the parent actually ended at line 40 reading, whether the child, where the child will start reading from, 41 or 0. One. Second question, if the parent pointer moves, go from 40, 41, 42, 43, 45, 44 line, whether the child pointer will also move or not.
Initially, the child is an entire copy, exact copy of the parent. So that answers the first part.
Meaning the pointer, the parts process system pointer, even that will be copied to the exact same player in the system table.
But they won't move together, right? Because it would be a deep copy of the pointer.
They will or will not?
They won't move together.
They will. They shouldn't move together.
Okay,
they
go
shouldn't.
good. Go ahead, write a code, and then get back to me tomorrow. It's like 3-line code for those who did the assignment and see. Sure, if you have any laptop, I mean, don't. Okay, you might or might not want to do in the class. I'm not going to stop you. It's up to you. But essentially, code it up. There is no, I mean, it's an open class at the end of the day. So, open files. Great. System and process. Those two things are there. And when you add fork, there are some behaviors which we don't understand yet. Write the code. Moving on to close. Okay, so open is clear so far, like per process and then totally open system. Good. Close files. So what does close files do is basically, again, when you close a file, when you delete something, the space does not go away. It will just be marked as free space. Anyone else can write it. So the requirement is that for a shared system, we are always talked about a shared system in OS in general. The operating system should not close a file if someone else is reading or writing it. What does closing a file means? Essentially, the operating system should not remove that entry from its in-memory data, from the system-wide file table. And for knowing this, like, that if at least one process have that file open, you need another data structure, which is called, or another element in the file struct in memory, which is called file open count. Okay. So this is yet another counter, which is a counter of the number of times a file is open. To allow removal, that counter needs to be 0. I don't know whether you have ever seen this, but when you start RM or deleting better in Windows, it says like a process is using that file. A file handle is in use or something. I forgot that actually. Removing, I actually encourage more in removing, and then essentially this is what it means. It might actually mean a second thing. So there are two counters. One is file open count that you actually saw just right now, which is basically related to system process table. Another one is related to hard links or even links, which is called reference count. If the references are still not zero, all zero, reference means like how many times the file is that particular storage space is linked on hard drive. If the reference count also is not zero, you cannot delete it. File open count is how many processes actually have that file open. File reference count is that how many actual files are referring to that particular storage location. Both needs to be zero for removing a file.
If it's zero, then how does it exist?
Huh? It's just a counter, no?
But at someone, I can see it means someone is reference. It's in some folder. If I'm seeing it,
Yeah.
that means some link is there.
Acha. No. So basically, think about the process. That's a good question, Vineet, but you have to think about the dynamics in the process. How do you remove the links? You do RM. How do you remove a file? You do RM. In the each RM, in the implementation, operating system will check if the reference count is zero. And in the last one, when the reference count actually becomes minus equal to zero, it will just free the space. So it will be an if-else statement. The removing the space will only be triggered if the reference count is zero. Complicated, huh? But these are corner cases that you need to consider. So, cool. This is like two data structures for open and close. Questions so far? Yes.
So like when you said that it returns an index into the array, it's the array of the processes open files.
It's the array of the processes open files.
Not the main global one.
If I recall, yes.
And that contains a pointer.
No, actually no. This has to be like the file descriptor that has to be finally resolved to the system-wide files tables. So essentially, it means that for one process, say you get a file descriptor of value 2. Will the other process get the same file descriptor value? Possibly not.
If it's the processes array, then it can get like if we open, like I think Deep was saying that, right?
Yeah.
That if 3 or 4 processes open, all of them can get 3.
Yes, so basically finally there will be resolved to the system-wide file table. That's what I mean. There has to be a translation function somewhere.
So it is the processes array of open files. That is the index which we get, and that contains a pointer to the system-wide.
Yeah. I'll confirm it, but yes, that is what I recall. At least in Linux, that is what is happening.
And the bookkeeping information is also process-wise. So
some are process-wise, some are system-wide.
The what we say offset of how much file is read, that will be
Process-wise, right? Yeah, that's true. Now you can logically think about the child and parent question, but still you need to check the implementation. Ultimately, code doesn't lie, and system behavior is not sacrosanct. It is not theoretical. In systems, you need to implement to know what is going to happen. That's a good, actually, that's a good lesson to be learned, because as Nisarg was saying that it should not happen, but let's just see whether it happens or not. Okay, cool. Now, once you open and close the file, knowing all these things, you have to access the file. That means the file pointer needs to move. Simple. There are two ways of moving. One is sequential, another one is direct. One is linked list, another one is direct. You'll encounter this abstraction everywhere in operating system. Both of them has pros and cons. For sequential access, you have read next, write next, and then reset, these 3 calls. Read the next byte in your file. Write the next byte in your file. Reset the pointer to the beginning. Yeah? And then a sequential access gives you a problem. The problem depends on the workload. If you sequentially reading a file that you often do while watching movies, or someone is using something called protobuf, like protocol buffers and so on, everything is sequential. Sequential access works wonders. If you have random access for doing a lot of computation, they have to actually do a lot of things like cryptographic computations, machine learning computations. They have to access a lot of memory everywhere. Random access, sequential access will not really work well. So for random or direct access, essentially file is viewed as a fixed length. So for sequential access, file is just a pointer. You do plus, minus, minus whatsoever. For direct access, file is viewed as a fixed length or rewrite used index and so on. Okay. Now this is something that you should know, that both of them are possible. Depends on your hard disk, depending on your operating system. Even different Linux systems have various implementations, but these two things are possible. These two abstractions that is provided to the operating system. Sometimes from the disk controller itself, not in your hand. Now n is a relative block number, but that n you have to remember like this. Like if an implementation has a direct access, it generally takes as a parameter a relative block number and not an actual block number from the file. Rest of the blocks are stored for bookkeeping. So for direct access, if I ask you, like, if it is like index 3 that you got, what is the actual index? You have to have 3 plus the bookkeeping blocks, whatever the bookkeeping blocks are. There has to be a translation module somewhere in the files, in the kernel space for the file system code. So with the accessing file after opening, just one point I want to make, this again extraneous point. If you have a direct access, you can simulate sequential access, because all you need to do is basically select access CP, the pointer, then CP plus 1, CP minus 1, and so on. If you have sequential, direct access is extremely difficult. Okay. Before going to directory operations, have you seen, I mean, when I told disk controller and all these things, I have some specific use case in mind. Have you ever tried to buy direct access instead of sequential access?
So don't SSDs have a roughly direct
Hardly.
access?
Direct access versus sequential access.
I meant an SSD.
Yeah, which is?
Which is direct access, and hard disks are sequential, roughly sequential. Like when you say buy, are you talking about actual hardware or?
Actual hardware. You are correct, but why?
Oh, why?
Because
SSDs are like RAM, like it's like RAM, similar to RAM, so it has random access.
Partially random access, yes. There is more to it. So there, I'll give you a funny thing. So it's first HDD, how it works. Very simply, have you guys ever seen record players, like even in movies, like those big disc? You put the pin and then it basically goes in. Any idea how record player works? Why it has better sound than digital medium? Never thought about it. But record players are favored by most of the musicians when they actually record the master record. So those grooves, this concentric circles on a record, that the pin that you put, they actually go on and on. That's exactly the same logic of hard drive. It basically just rotates and rotates and go to the right concentric circle where the data is stored as grooves, essentially, in record player. Means you need to do sequentially, because you cannot go to the final concentric circle, the outmost concentric circle, without going over all the other concentric circles. That's a sequential access. For your direct access, you have SSDs, which is technology similar to RAM, but it's persistent. There is something called NVRAM, which is non-volatile RAM, which is actually a dual of RAM, which is persistent. SSD is an approximation of that. There are ideas of NVRAM-based operating system where the whole operating system will run on RAM. Fast, extremely fast. But it didn't happen. Rather, SSD happened due to physical, and that is electronics part. But essentially, direct access is the holy grail. You pay good bucks for getting that. Sequential access is cheap, but then again, this is what we got. So after opening files, you have to rely on the underlying hardware and the controller and everything to access those files. That's all on that part. Finally, the basic operations. There are 6 basic operations on directory. We talked about file. Directory is something that we'll just touch and mostly stay within the file domain for the implementation. So first one is searching for a file. Second one is because searching for a file needs to be done for opening and opening and closing essentially. You need that functionality from the directory. Then you have to create a file, or within a directory, you need to create a file. You need to delete a file, list a directory, rename a file, and traverse the file system. And by traversing, meaning enumerating all the files in the directory. Now, reading and creating a file, deleting a file, these actually are different from the create operation for file, because you need to make directory entries when you create a file. That's what I mean that these are basic operations on directories. Once you create the directory entry, then you have to read and write and do everything on that file level. So that is handled by the file creation operator. First you create directory, then you create the file. These two are different modules in your kernel space. Now again, renaming a file, why renaming a file is important? Because the devil's advocate argument is that you can rename a file, but just moving it. Create a new file, reading and writing there. No? Expensive. Disk is expensive. You reduce the number of disk write, you will have 100 times speed up. Happens. So renaming a file, just change that directory entry. That is the name, just change that name. You don't need to read, write, you don't need to do anything. You have to be really smart. Again, this is not rocket science. This is not sacrosanct. If you come up with a better idea tomorrow, if you're a Linux developer, Linux will actually take it. Even today, many modifications are made every single. Otherwise, why do you think there are so many releases? Every 2 years, Ubuntu has a release. Why? Problems are not solved. And here the problem means performance. Okay, and then that basically searching, creation, deletion, and specific for directories, listing a directory, renaming a file, and traversing is something that directories need to have. I also put the comments here. You should have known this from your assignment, but this is just some comments put on the slides, which are extremely important and something that you should know by heart. Okay. I have a question now. If you don't have any question, do you have a question first? When you are doing move, MV, are we renaming a file? Are we copying a file?
Rename, I guess, it works much faster than copy.
So I think it depends on the directory structure and how from where we are moving to where.
Because from what I've seen, sometimes a big file is just copied in an instant, sometimes it loads and takes time.
Why?
I think it's something related to moving up a tree or down the tree, then it's fine.
The directory entry manipulation. Because moving a file is not only changing the name, you have to change the tree itself.
Yeah, so-
If in the same directory, like this, same level node, na? For other, you need to balance the tree. And if that's a huge directory, it will take time to balance. Also, you need to, so that is if in the same partition, so they are like, if that question is a little bit involved. There are two cases. One is in the same file structure, then you just need to rebalance the tree in the worst case. In the different partition, need to copy. There's no other way.
Before we move, there's like no way to know if it will move the entire file or it will just change the name.
Exactly. I mean, you can surmise, but either way, if you want to copy from your C to D partition, I mean, you need to actually copy the file, create a node, and do the whole rebalancing. That will take time. That's why I told when you are actually seeing questions, think. It's not as simple as it happens because there are always corner cases that will mess your code up. Any questions so far? Yes.
When you say balance, you mean just like reorder, like change the links and the nodes, right?
Exactly. And by the way, the balancing on change the order is not as simple as you think it will be. You know, the file system is corrupted message. Have you guys ever have that? The file system is corrupted, you need to fix it using FSCK or you have not.
Yeah, it happened, and it happened on an exam day.
I'm so sorry. I'm so sorry. It's a really bad error. I hate this error, and there are two reasons for this error. One, which is killer, that your hard drive or your SSD is corrupted. What is corrupted? Physically, it wore down. You cannot do anything about it, right? It wore down. It cannot hold the bits. It flips the bits. And essentially, that means that your file system information there is gone. There is even a worst case. If those bits which got corrupted are in the directory structure. You see what I'm saying? So what FSCK does is try to actually retrieve the data as much as they can. They first check whether the pointers are working. Okay? If the pointers are not working because some of the corruption, like you just kill the program because it's hanged, like your Chrome. But Chrome was basically writing a file or doing something that actually created an inconsistency in the file system. Even when moving a file, the pointer is not allocated properly. A lot of things might happen, as you can imagine. I'm not going into details, advanced stuff, or think about this corner cases. But the point is that those are easily fixable. You traverse the T. If there is like a child without parent, you just remove that and mark it as free space. And remove that pointer. There should not be any null pointer. There should be any dangling pointer. There should not be any free space like without parent. Simple cases, right? Like making a tree, essentially. However, the problem happens when your hard disk is corrupted, and then it's on your luck where it is corrupted and what the file system recovery can do. The last bit before we move on from API to the implementation, system-related functions. There is a big business that you might not be aware of or might be about retrieving deleted data, both legitimate and illegitimate. Legitimate is essentially when you deleted a whole, or your hard disk got corrupted, or you deleted a whole directory. How do you retrieve it? There are open source tools, there are paid tools to do it. How do they do it? Deleted it, it's a free space.
Free space has some background.
Pardon? Yes, Animesh, speak up.
So like free space has some information from which you can like like it's something when I say it's free, like no one else is touching it, but whatever is written over there might still be useful.
Perfect, not useful. It's the old data. Like you deleted it, true. But all the operating system did is marked it as free. Someone else can use it.
But like, even if I have something saved, so it can be like over time bits get flipped.
Exactly. I agree. So essentially it's marked at free. That means anyone can write it. That does not mean others will write it. It will totally depend on the process and the load and whether they would need it and all these things. That's how you can retrieve some of the data. And then there is another big part, which is to make sense of that data. Because you ultimately retrieved the actual, like from the controller or disk, you ultimately got just the bits and bytes. How to make sense of it as files. There you need to use heuristics, sometimes machine learning, to know that how much of that data is your JPG and what is the next bit for your text file.
I guess they use the magic bits because that's how the file command works.
Magic bits is a hit or miss.
Yeah.
And not all data structures have magic bits. You can also remove the magic bits to secure your data.
Yeah, if you're securing your data, you might as well create backups.
Yes, people don't. Anyhow, the part is that for deletion, things just got marked as free and that still has valuable data. The solution is using Shred, S-H-R-E-D tool. It will kill your hard drive eventually. But what it will do is that it will allocate first, it will write and rewrite zeros or random numbers on that free space on your file, and then it will unlink it, remove it from the directory. Why it will kill your hard drive? Because you're reading and writing different parts of hard drive continuously. Physically, it will be wear and tear. Okay. So now you know 3 commands for deletion: rm, unlink for unlinking the directory structures, marking as free, and the third one, shred. Comes pre-installed, at least in Kali. I don't know in Ubuntu. Perhaps it does. Okay. So file system related function. Now we are going into the second part about different implementations, different algorithms on how to actually implement at the kernel level these different functionalities that we talked about, data structures that we talked about.
So
yes, go ahead.
I wrote that that fork thing. Apparently, the child and parent actually share the offset as well.
So if the child moves, will the parent move?
It is.
Nisarg?
In fact, I actually read the document.
It was a tricky question. Now you find out why. In the documentation, just search around in Google, and in documentation, you would actually know that what is the exact implementation, how the fork is happened with system table. It's a design.
In man fork,
what is
it says that.
Read it up, otherwise I'll post it later. But seriously, this is an advanced one. I just asked that question to make you think, as Nisarg rightly told. I applaud that should not be the related behavior, right? Parent and child are sort of independent entities. But it happens, and that has to have some reason, some performance-related reason, or some workload-related reason. What is the reason? Everything happens for a reason. These are design decisions. Again, someone else might implement it in such a way that parent and child pointers will move separately. These are 2 different pointers, but it does not. Why? And I would request any of you, I can name names, request any of you to actually post it on MS Teams. I'm curious to know that what you would come up with or you would find. I definitely have some idea. But let's take it as homework. You know the design decision. Why? We don't know yet. Let's see. Okay, now implementation. Yes.
It's very much similar to what COW is like.
Yep. It's like copy on write, and that's why fork is based on copy on write, as I wrote a long post there. Think in those lines. Writing is expensive. So how to reduce the performance? And if for that you have to, you means as a OS developer, have to sacrifice some sort of usability or utility. Think in those lines. I think it's a cool question. Check it out. Okay, now for knowing the functions, we need to have some background knowledge and data structures. The class is almost ending, but let me actually give you the background, the first background, which essentially is you'd actually know about 3 things in the implementation. First one, you have to how to implement this calls, open, close, etc. for API and directory. Second one is how to allocate storage to the files once you created the files. And third one, how to manage the free space. Okay. And we'll divide this part of the lecture into these 3 questions. So first is definitely the implementation. Implementation of the calls, function calls that we talked today. And for that, the background first that I want you to know is disk addressing. I'll stop there after this. But the point that you need to remember that I don't care about hard disk or SSD as a kernel developer. I cannot. If tomorrow NVRAM comes, tomorrow some different hard drive with different, like even hard drive have different flavors, 5600 RPM, 7200 RPM, this and that. I cannot care about all those things. I cannot write an operating system for your computer. So for that, essentially, we use something called this logical block addressing, LBA. Logical block addressing export your hard drive as a logical array of blocks, like 0 to n, marked as 0 to n. We're talking in the kernel level. Okay, kernel sees the hard drive as 0 to n. Hard drive, if it is a hard drive, sure, it will be, the controller will translate the 0 to n to actual wherever the data is. Operating system for you as developers, you'd see it as 0 to n. And these blocks are the smallest unit of transfer. Meaning that each one of the 0 to n array of blocks, like this actual blocks, will not be, or generally are not will not be. That's a strong statement. Generally are not 1 byte or 4 bytes, much bigger than that. Why? Each of the array element is not small, they're big. Why?
Reduce the number of disk 6.
Pretty much. Reduce the number of disk 6. And here the word alignment comes into play again when you store the data on disk a lot. So we call the blocks in the secondary storage as physical blocks. I'll just finish with an analogy. So in the memory management, you had frames in your RAM, and then you have virtual address. Here you have the logical block at LBA, and then you have the physical blocks. Here means the file system. But because file is slow, you need to do a lot more stuff, and we'll talk about that. Okay. It's exactly 12 questions.
So like we can have different hardware, as you said, right? Hard disk can have SSD and different kind of stuff.
Mm-hmm.
So like the abstraction levels can like basically optimize on what, like we have like 2 or 3 options, right? So
you have more than that, because think about the hybrid caches. Think about the different controller types. So you know this PCI and SATA and all these things, this is SATA and this is not. All it tells is that how it will export your drive, like whatever you bought, to the operating system. Some boards support SATA, some boards does not, because ultimately the controller needs to translate this whatever you have to that blocks. If the board does not have the hardware to do that, tough luck, it is not compatible. And these are just NVNI, in ME, SATA, these are all protocols to actually do this logical block addressing. It's not an easy problem, not something that we worry about, it's hardware guys. Ready, come in?
Motherboards have their own processors and caches to do that stuff.
Yes. And your device driver will talk to the controller with the exact same, like that's why you need separate device drivers. We'll talk about that from the next class onwards. That part is also in the background. But now the things become simpler, right? Because now you don't really need to talk about hard drive, SSD, anything. It's just logical blocks, 0 to n. Yes, someone has to write the device driver. Some of you might will, but then you need to know the whole thing in hard disk then, not before that. Okay, that will end this class. Just remember that, and we'll talk about it, but this logical bit addressing, not only for hard drive, also for your webcam, any peripheral, because this is such a powerful and beautiful construct. Just an array of bytes for reading and writing. Nothing more, nothing less. Any peripheral, you have your USB or anything, this abstraction will work. And even your dongle, your Bluetooth, anything. This is the abstraction. You want to create a new device for tomorrow, doing something really cool and doing ML on disk, just putting a machine. You have to ultimately give this read and write interface.
This is data transfer abstraction, right?
Yeah. This is the most used data transfer abstraction. Any question? Okay. Thanks a lot for joining, and we'll talk tomorrow. Just a note is that we might have to have extra classes that will be online. We'll record it and put it there to actually finish it because we don't have much time left. But if that happens, we'll let you know. This extra class in lieu of Holi. At that time, we missed one. But now we'll continue anyways. Okay. Thank you.
Thank you, sir.
Give the answer on MS Teams. Whatever you find. I mean, there is some rationale. I mean, these are not stupid people.